So you all can see the screen, right?
Yes, sir.
Okay. Yeah, so I think most of the questions that were asked in the def- uh, in the discussion forum, it was more or less they were related to how to uh, what are the relations, what are the between this elasticity moduli, right? So yeah, I have downloaded this photo from internet where you can see that these are the all possible relations. So here the notations a little bit different. For example, here this Poisson's ratio or Poisson's ratio, we used to call it as we used to yeah, so we used to denote it as with mu, right? So but here it is written as sigma, and the bulk modulus is small k, shear modulus is mu as it is. Lamis constants, this is the same, right? So there are other Lamis constants which is mu, and shear p wave velocities we call it as vp, and s wave velocities we call it as vs. Yeah. So, and one question that Suraj asked in the discussion forum is that how come this Young's modulus E is written, can it be written like E is equal to 2 mu? So it was written in the lecture notes or in the presentation the sir shared, right? So the thing is, uh, this term, this Poisson's ratio, is applicable for 2D or 3D material, right? So if you have a material which has only one dimension, so for the simplistic model, so this Poisson's ratio becomes 0, right? Or maybe in materials where you have a very Poisson's ratio is very near about 0, then your equation becomes like that, right? So this is what was written in the presentation slide. Is this all right? So I think that answers your questions, right, Suraj?
Yes, sir.
Okay, yeah. So these equations can be derived. So I have already uploaded one uh, material in the OneDrive folder. See, you all have access to the OneDrive folders, right? Hello? Do you have access to the OneDrive folders?
Sir, I have never tried to.
Okay, so you can find it here in the problem solving session tab. So if you open that, so it will, you have to click here and it will redirect you to somewhere here, right? So in the presentation folder link, if you open that, you will find all the PDFs of the code work that we do here and some materials that I have started to upload there, right? So you can download it from there and read it by yourself, right? So these are just for supplementary material. So this, in this book, it is written like how we are getting the Hooke's law, and from that Hooke's law they have derived. So we are familiar with the Hooke's law, right? So f is proportional to x, and now we have a constant that is spin constant. So it gives you the one dimensional what should I say, elasticity equation, right? So if we go on, so here this equation tells us about, so this f becomes trace here for two-dimensional case, and now we have the Young's modulus, so it replaces the k and this becomes the strain, right? So I have already showed you like how this matrices can be formed from a two-dimensional deformation matrix deformation. So from that, so xx means only the diagonal terms. Are you with me there? So are you getting this? Right? So if you do not understand anything, please stop me there and ask questions. All right? So I guess there are only two people today. So Sujesha and Suraj. If you do not get any, if you have trouble understanding something, stop me there. All right?
Okay, sir.
Yes, sir.
Okay. Yeah. So we all know, right, how the deformation matrix is written for a two-dimensional case, or do I have to go with it again? You want me to go with it again?
Yes, sir.
Okay. So this is the case. Like here, it will be sigma xx. Here it will be sigma yy. Here it will be sigma zz and sigma xy, sigma xz, sigma yx, sigma yz, sigma zx, sigma zy. All right. So this is how the deformation matrix. This is actually the strain matrix, a stress matrix. So likewise, the deformation matrix you can write like this, right? Xx, xy, xz. All right. So we are only taking the terms this one and this one. So this is replaced by uxx in the literature that I shared with you. So yeah, so this is it. All right. So from there, Poisson's ratio is basically defined as the ratio between two strain that is orthogonal to each other, right? So exx, and what is the, like, if I draw the coordinate system, so along this axis the strain will be exx, right? Along this axis it will be eyy, on this axis it will be strain. It doesn't matter where you put this, but they all have the orthogonal relationship, right? So the ratio between that with the negative sign is basically defined as the Poisson's ratio, right? We know all this, right?
Yes, sir.
Yeah. So from that, uh, so yeah. So for a homogeneous situation, homogeneous condition, the sigma xx will be equal to some, say for example, a force that is P, or maybe it can be equated with pressure. And so this, so sigma xx is replaced by P. So as we have seen earlier, that mu xx is basically sigma xx over E. So, and with using the Poisson's ratio, we can get these two relations, right? Is it okay until now?
Yes, sir.
Okay, yeah.
Yes, sir.
So after this, so everything is fine when we consider the elasticity of a material which is one-dimensional or maybe even two-dimensional. But it is difficult for, because to apply those relationships in real life, because most of the time we have materials that we deal with even in earth science, or we call it in material science or mechanical engineering. So in all those cases we always deal with 3D bodies, right? So the Cauchy and Lamy in 1852 and 1822, they have derived a relationship where you can actually, without using one single constant, which was Young's modulus here, so without not using that, you can write the equation of elasticity like this. So what does it mean? So this is the force term as usual, and there are two different strain terms, right? So what happens here? So from this matrix, these diagonal parts, they have the index notation EII, right? Or maybe you can write it as EKK, right? So XX, so K becomes X. So all these two indices becomes equal. So the whichever part is in the diagonal portion of the matrix, that gives you EKK, right? And everything else gives you EIJ, right? And if you multiply a Kronecker delta with it, so it makes everything except the diagonal term 0, because that is how Kronecker delta is defined, right? If I is equal to j, then this becomes 1, otherwise it becomes 0. All right. So with the off diagonal components, you have to have a constant which is 2 mu, and with the diagonal components, you have a constant which is lambda. So these two are called Lamis parameter, and from this equation we can write like here sigma xx. If you just replace the ij with xx, so this uij, this becomes uxx, and this is 2 lambda and 1. So this will also become xs, right? So this kk becomes xx, so you will get one contribution from this lambda, like, and this is there, this is here, and other than that, you will also get uyy and uzz, right? Do I have to write it down, or are you getting it? Do I have to write it down? Hello?
Sir, please repeat what you just said.
Okay, I'm showing it here. So this is the equation. This is the equation, right? So what happens when I becomes x and z, j becomes x? What happens? Then sigma xx is equal to 2 mu xx plus lambda. So this will be what? So this will be 1 for all the three cases, and this will be sigma xx plus, not sigma, sorry, epsilon xx, epsilon yy plus epsilon zz, right? Right. So from here we get 2 mu plus lambda epsilon xx plus lambda into epsilon yy plus epsilon zz. All right. So this is how they derived it, right here. All right.
Yes, sir.
Okay. So this is
Okay,
how
so
it
this
derived.
is how it did.
Yeah. So this is how it derived for all the possible cases, and from that we come up with a relation which is somewhat like this. And when you solve for it, you will get one relation like this. So this is actually um, part of the constitutive relations. All right. So so these are some strange notations. So I have uh, included this link as well. I don't know why it's not opening. Yeah. Yeah. So in this link, you can find all the notations that are related to us, and it is more like the notations that we use. All right. So, and this is how, like this, in this PDF, you will get all the necessary information that is required for this kind of derivations and all that. You don't need all this. If you feel interested, you can just go through it. If you find any problem, then you can ask. Otherwise, it is not really required at this basic stage of structural geology. But this is
Okay,
but
sir.
but that is there. So if you want, you can go through this, or maybe there are other materials also available online, so you can go through all these materials.
Okay.
Sir, I have
Yeah,
a doubt.
yeah. Go on, go on.
So, I am feeling difficulty in understanding elastoplastic rheology.
Okay,
I
I
don't
am
understand how graph is drawn.
okay. I will be coming to that, because the next part I'll be covering the rheological models. All right. So this material is also uploaded on the OneDrive folder. So I will start from the basic, right? So I'll start from the beginning, that what is the linear elastic spring, and from there we will go to the
Okay, sir.
composite models. Okay. Yeah.
Okay.
So in the linear elastic spring, you see this is the strain. So this is how I actually has just described, like in the linear elastic case. So this stress, this force term is proportional to the strain, and it is related to some constant 1 by E. So this is Young's modulus. This is how it is related. So this is what we have learned, like in the school, in the plus 2 level, maybe plus 10 level, maybe, about this elasticity and the basic Hooke's law of these things. So there is another thing that what if the response of the material is not linear, right? So if the material is not behaving like a spring, so there is another simple model for that, that is called the viscous model, right? So one is the elastic model, linear elastic model, and the other is the linear viscous model. So in this, what is the difference between these two? So in the first model, uh, strain is proportional, or stress is proportional to the strain. So just note that there is no dot on the top of strain, right? But in the viscous model, there is one small dot. So that means that the strain is proportional to the strain rate. So another factor is coming into play here, that is the time factor, right? So you have to differentiate the strain with the strain rate, with the time. Differentiate the strain with time, and then we will get the strain rate. So now the proportionality constant changes here, so it becomes the viscosity, right? And this mostly a typical response, as written here, for many fluids, right? In terms of water, oil, so this kind of things, they behave in this way, right? So, but surprisingly, for our geological materials, we don't, we don't have this kind of simple models. So what we do, if we want to explain these things, we see there's some kind of complex models. How is that? They basically, suppose you have an elastic model and you have a viscous model, you just couple these two, right? You have to use it in a way so that you can explain the response, right? So there are Maxwell model, Voigt Kelvin model, and then there is Bingham model, right? So in Maxwell model, so the spring and the dashpot. So dashpot is basically a representative of the linear viscous rheology, and the spring is a representative of linear elastic rheology, right? So if you connect them with a series connection, like we have learned in the electricity classes and back in the school days and college days, so if we connect them with a series connection, then this equation becomes this, right? So what we have to do, you have to just differentiate the uh, say for example this part, spring part, and then you will get this equation, and just to add them up, right? If you add them up, so this becomes the Maxwell model equation. And the other model is the Kelvin or the Voigt model. Here the spring and the dashboard, they are connected in a parallel connection, right? So what happens if you apply stress, so this whole body will expand, right? And the response will come both from the spring and the dashpot as if they were connected in a parallel way, right? Like how we do for the how we do the connections for the resistors and capacitors, like that. Okay, but what is the difference between two? So let me go to my one more. If you have a dashpot and a spring connected in series, and we apply some amount of force, right, or maybe some amount of stress, whichever suits you. So if we apply that, what will happen? They will instantaneously, the strain will start building up, right? So instantaneously the strain will start building up, right? So this is actually the initial stress, if there was any. So I am considering the sigma 0 is 0 here, so that's why I have drawn the curve from here. So it instantaneously it will start, and when you stop the stress, so it is written the stress is removed. When you stop the applied stress, so it will recover instantaneously. So what will happen? This dashpot, so if the spring is somewhere here, at later instant of time, if the spring is somewhere here, so it will stop then and there. So it will just drop, and then you get nothing if you do not apply stress. All right. So the strain, the response of the material stops as soon as you remove the stress, right? But in case of Voigt or Kelvin model, the situation is little bit different. Why is that? So whenever you so these are connected in parallel, right? And you're applying some force here. All right. So when you pull this string, spool this part, what will happen? Due to the viscous drag, the spring won't react instantaneously. All right. So it will be somewhat like this. And then you remove the stress, you stop applying sigma. So what will happen? So it will try to, the spring will try to contract, right? It will try to get back to the initial position. So now, say for example, if the spring initially was like this, and after applying stress, the spring becomes something like that. So the dashpot is connected. Yeah. So the spring becomes something like that. The dashpot is here now. And so, but now you stop applying this stress. So what will become? It will contract, right? The spring will contract. And but there will be again, like when you started the motion, there was one resistance from the dashpot. So there was some kind of decay with the not the decay. The development was not linear, right? So, but with the decay part, when the spring started to contract, it will again receive resistance in this direction. So it will try. So this part is trying to go back, and there will be again some resistance here. So what will happen? The relaxation or decay will again be nonlinear because of the viscosity term. You know what is a dashpot? I'm sorry, I should have asked the question first. You know what is a dashpot? Hello? Sujesha?
Hello.
Yeah, so you know what is a dashpot?
Yes. No, sir. A little confusion.
Sorry?
Not clear, sir.
Okay, so it's like a kind of a device that that is installed in the doors. All right. So so this is some kind. So it's device. It's this kind of device and installed in the doors. All right. So there is one
Yes,
piston,
yes.
and you have some kind of fluid inside, like this one, right? So you have some kind of fluid inside. So that
Okay.
actually provides the viscous part.
Pressure.
Yeah. So you see, there is a spring and the dashboard. So this is how. So these are actually hypothetical models that are
Mhm.
used in case of explaining the rheology of complex geological materials. All right. Yeah. So there is that, and I think there is some connectivity issue from Suraj's part. Yeah. So Sujesha, can you mute yourself? There's some kind of noise. Yeah. Thank you. Yeah. So yeah. So the difference between Maxwell model and the Kelvin Voigt model is that the reaction time, right? So this is the reaction time. All right. So when you stop the the, or maybe the so the recovery response, you can say the recovery response is longer in case of uh, Voigt, in case of Kelvin Voigt model, right? But in case of Maxwell model, so the recovery is very instantaneous. We have a very little time for the recovery response, right? So there is another thing, another model, that is Bingham model, or the Bingham plastic, in which we just use a spring and a blocks. It is not here. All right. Yeah. So this is there. So elastoplastic rheology. So what happens in this model is that, okay, so what happens is that you have a block that is connected to a spring, and you will just pull the spring and the block will slide. All right. So what will happen when you you know uh, pull the spring? So the block won't move instantaneously, right? So there is some friction. So you have to but the strain will be there, but that will be uh, stored on the spring. So, but this block won't move. So after a certain point of time, when the static friction, the energy is, if you calculate the energy of that spring, and so that will be equivalent to the energy that is required to slide the block. You just have to overcome the barrier, the friction barrier, then the block will slide, and then you will have a permanent release of strain. All right. So this is how the earthquake actually happens. So this Bingham plastic model, the elastoplastic model, we can explain how the earthquakes happen. All right. So you see, we have pulled the string, but there is no slide, and now it's slide. The slide happened, and so here this one release of energy, one point of release in energy at T5 instant. Right. This is how this earthquake happens with elastic loading and then stress drop, elastic loading and then stress drop, elastic loading and stress drop. Yeah. So these are the different models that can be used if we want to explain the behavior, rheological behavior of Earth's crust. Right. Yeah. So
Okay.
yeah. So that will be all about rheology. Sujesh, do you have any question regarding this part? Anything more about rheology?
Yeah, need to stress that I am last few days with some busy with family functions.
Okay. Yeah. All right. So
Okay.
I see Prabhakar joined. Yeah, Prabhakar. So you joined late today. Can you unmute yourself, Prabhakar? Okay, yeah, I don't think so. All right. So today we just covered with the rheology portion, I think, and then there is, so with all this information, if we want to recreate the processes that happen in natural scale, on in art scale, if you want to replicate the process in the lab, what we do is we perform experiments. So we vary the parameters. Say for example, we vary the pressure, we vary the strain rate, we vary the temperature, and this is how the response curve looks, right? So if you increase the pressure, confining pressure, so for example, so the the material will become will feel more compact. So when we increase the pressure, it's just to confining pressure is just to replicate the depth of the sample where it is present, right? So if you increase the pressure, so sample will go more deep down inside the earth, and then if you deform the sample, then this is how the failure curve looks, right? So with the temperature, if you increase the temperature, that have different responses, and if you increase pore pressure, you have different responses. So yeah, there's that. And so these are all from the rheology part. All right. So Prabhakar, do you have anything to say, or because otherwise, okay, I don't think so. Yeah, great. So yeah, the material I already shared with you, and in the next part we have here deformation mechanisms. Yeah, so I think I will start with deformation mechanism today. So you have any idea about how so whoever in the class, you have an idea how actually this deformation that in art actually takes place from a microscopic point of view? Do we have that idea?
Which one, sir?
uh, how the deformation inside the art happens? I mean, what is the mechanism, how it happens? Do you have that idea from a microscopic point of view? Okay, I will explain it. All right. So if you have a mineral, so what is the mineral looks like? The mineral looks like an array of atoms, right? So this is how a mineral looks like at a microscopic and very, say for example, micron scale, you may say. So this is one lattice, right? So this is a regular 2D lattice, but this does not happen in the natural case, because in natural case we have tetrahedron, right? Silica tetrahedron and those like that. So they are connected in some way, and you have the lattice of this, right? So in a three-dimensional space, these points are oriented, and in nature it is very difficult. Suppose in SA, for example, if we take the example of SiO2, it is very difficult to have pure Si and pure oxygen in all over the lattice, right? So what we have impurities, we have ions, right, inside the lattice, right? Or maybe in some places, in some cases, we may have a missing atom, right? So these are called defects of the lattice, or crystal defects. So defects can happen due to the presence of something, or maybe the absence of something. So something, I mean the atom, that the place it it is supposed to be. All right. So these defects can be of various kinds. So it can be point defect, and it can be line defect. All right. So it is covered later. Yeah. So and it can be, of course, a surface defect. So if you have in a lattice, if you are missing one crystal, or maybe you have a, so that will be termed as vacancy. And if you have something there present which is not supposed to be there, that will be called interstitial. All right. But in case of line defect, suppose you have the point defect in a three-dimensional array. Those point defects are aligned along a particular line. That line preferably has to be one of the crystal axis, or maybe not, because sometimes you may have a line defect which is not exactly the crystallographic axis of those crystal, right? So yeah, so those are termed as dislocations, right? So if you have a material and along that, we have a picture of line defect here. Yeah, so these are point defect. We have vacancies, right, in the crystal array, and maybe some interstitials, ions which are not, so these are not regular ions, these are something different, something bigger. So this creates a kind of strain inside the crystal, right? So it is there, right? And if you have like this one, you see this defect is basically running along this line, right? So this will be in 3 dimensions, this will be called in 2 dimensions this is line defect, and if it extended in the 3rd dimension, it will be called surface defect, right? Yeah, like this one. So surface defect, yeah, like this one, right? So it is extended in the 3rd dimension, right? Yeah. So is this clear that how the defects are present within the crystal? Is this clear?
No, sir.
Sorry,
Blank screen. Blank screen.
I cannot hear you. What did you just say? Hello?
Yes, yes, clear, sir.
Clear, right? Yeah. So these defects are already there in the minerals. So, and when we apply stress, so those defects move, right? So those defects move in a way, they create entanglements, right? So if you have a grain like this, and then you have maybe a line defect like that, right? And maybe another defect like that. So when we apply stress, what will happen? This lattice, the lattice inside the grain will try to reorder themselves. So as a result of that, these defects will move. So it may move here, it may go there, this one may go there, and this may come there. So at the end, after some time, so there will be some kind of entanglement of the defects within the grain, right? So after that entanglement, that is not really, you know, what's desirable for a mineral to have a, for a crystal to have entanglement inside that. So what will happen? It tries to reset that crystal arrangement, retrace that lattice arrangement. All right. So when they reset that lattice arrangement, so the entanglement is gone, and you produce a grain wall or a grain boundary. So initially it is subgrain boundary, and after that, when you increase the misorientation between the lines, so what will happen? It will, after some kind of more mismatch of the orientation, produce a grain wall, right? So this is how recrystallization happens. So you have a grain, you apply stress, So the dislocation entanglement happens, and after that new grains form. So whenever new grains are forming, we call them recrystallization. So that's why if you have a big grain and if you have recrystallization, so the grain size will reduce, right? So you have one grains. From that, if you make 4 grains out of that one grain, so grain size will definitely reduce, right? That's why in natural mylonites you see fine grained rock, right? So the rock in mylonites or ultramylonites are very fine grains. It's different than the host rock, right? Yeah. So yeah, so the dislocations can be an edge dislocation where the lattice is just so the lattice is moving just like it's just like sliding along along the slip plane. All right, so this is the slip plane and this lattice, this portion of the lattice is moving along the slip plane. So these are called edge dislocations. But if it twists, say for example like this one, right? So the upper part of the lattice, they just twist just like tearing a paper, right? So when you tear a paper, what will happen? The tear goes inside, right? So it is here initially. So when you tear the paper, so this goes inside. All right, this kind of dislocations are called screw dislocations. All right, and so there are dislocation movements, as I said. So if you want, if the dislocation or if the dislocations are want to avoid a present already present interstitial, so it has to climb and then it will just glide and again climb, it will just glide. So this is a simplistic diagram, but climb means basically you are changing the array where the dislocation were previously in, right? So there is a plane and dislocation is moving along that plane. You find an interstitial or some kind of hindrance and you just change the level. Like it can go down as well. So it's not like it can always have to go, it has to go up always, it can also go down. So with climb and glide, dislocations move. All right, so there are some beautiful diagrams that is pretty much self-explanatory. So yeah, if you do not have any question from this slide, I will move on to the next one. All right.
Okay.
Okay. So there are different kinds of deformation, in which one is the cataclastic deformation and intracrystalline plasticity and diffusive mass transfer. So I most of the time in the previous slide I was talking about intracrystalline plasticity. Right. So what is cataclastic deformation? Cataclastic deformation is basically uh, kind of the grain crushing, or the kind of when the rock is still in a brittle phase. So what does it mean by brittle phase? That the rock will show a behavior. Okay, why is it black? Okay. So if the rock is showing a behavior like that, so after the yield point this just drops. So this is stress and this is strain. So after a certain point of time, after the attaining the peak stress, it will just drop. So we will call this behavior as brittle behavior, right? So if brittle behaviors happens, fractures, grain crushing, these kinds of things happen, right? This kind of things takes place. So in that case, cataclassites are formed. All right, you can see like in this image, you see the grains are showing very sharp edges, so they are actually broken, and there is kind of cement in between that is bonding these things. All right, so these are the localization of cataclastic deformation. Yeah. So but in case of Okay, so this slide is mostly about cataclastic deformation. Yeah. So here are some examples, like when this happens at a very large scale, we see this kind of landslides or this kind of flow, right, granular flow. But in the small scale, we see this kind of brittle bands, right? So this is also an example of cataclastic deformation. You can see that the grains are being fractured, right? This is A, this is B, this one is C, D. So this is the way how deformation has proceeded, right? So this is how the grain fractures had appeared in this B section, and then in C section you can see the fractures are widened, and these fractures surfaces are filled with some material, right? So yeah, that will be mostly about the cataclastic deformations. So yeah, I'll go to the intracrystalline plasticity now. So as I was talking about dislocation and deformation happening at a microscopic scale. So one thing, so this is Orwan first introduced or maybe explained how intracrystalline deformation can happen, right? So what he did, so he defined a single dislocation as one basis, as single basis of the overall deformation, right? So do you know what a basis is? So basis is like a unit vector, right? So we all know what a unit vector is, right? Okay, I will assume that we know what unit vector is. Yeah. So basis. So with the Burgess vector is basically the basis of a deformation, right? So with defining the Burgess vector, we can actually mathematically, identify what are the different parts of and how to mathematically express the dislocation, right? So yeah, so if a small region of the part of a crystal that is undergoing deformation, and with a basis of Burgess vector, so we can define the dislocation density as the 1 by L square, right? And the incremental strain for that small movement will be defined as something like this. So this is Orwan's equation. So this will be strain rate epsilon to the power epsilon dot. So this is Orwan's equation, which defines how dislocation should move. All right, dislocation behaves in a very microscopic scale, say for example. So dislocation as a whole, it's just like a, every mechanical what should I say, mechanical processes that if you want to push something, you have to, so there is a friction present, right? So if you want to push something, you have to cross that barrier, right? So dislocation also doesn't happen by its own. So on its own, it doesn't happen on its own. So what we have to do is you have to cross that barrier, right? Cross that barrier, after which dislocation will move. So that can be applied with application of that can be supplied by the application of stress, or maybe increasing the temperature. So when you increase the temperature, the atoms at the lattice point, it starts to vibrate more vigorously, so it is easier for them to move. And when you apply stress, so it will feel that kind of need to readjust themselves, and then also you can cross the barrier. All right. Yeah. So these are the equations which defines how dislocation glide and dislocation climb would can be represented in mathematical models. But yeah, I mean, there are some terms missing, like in the recent publications. If you go to those publications, you can add like a term of water fugacity, or you can add some term of say for example, you can change this term and have like different activation volume you can add here, and you can change this Q, which is the enthalpy. So yeah, so these equations are actually what should I say, empirically deduced. So these values of these constants are not fixed, so only R is fixed, that is the constant, universal gas constant, and there is T, this temperature in Kelvin, that you are supposed to know that temperature in which your deformation is going on. And the other parts of this equation, for example, activation volume and the enthalpy, these are derived from experiments, right? So you perform series of experiments, and from the plots you calculate these parts, all right? So yeah. So yeah, I am actually going through all these things so that you find it easier to go through the lectures later, if you haven't yet. All right. So yeah, so I will now go to the different kind of recrystallization that happens, right? So suppose you have a coarge, right? If you have a aggregate of coarge, so when you deform a quartz grain, what will happen? Initially, initially the grains will form some kind of bulge. Initially, they will form some kind of, can you see the bulge here? Hello?
Yes, yes.
Yes, so bulge is just like a lump, right? So when you have all the dislocation tangle, so as a process of releasing that strain, releasing that entanglement, some kind of appendage from the grain will form outward, all right? So that in that new grain, so initially you will have a grain which have a lot of dislocation entanglement, right? So, but when these bulges will form, so for example, from this here, this bulge will form. So the entanglement will still be there, but this part will be more or less strain free. So this statement is not entirely true. Some amount of strain will always be there, but this bulge will be more or less strain free, right? This is how it creates a new strain free domains inside the grains, right? So after that, if the deformation is proceeding, and the deformation is and accelerating, or deformation is there, what will happen? That some part of the grain, so after forming those bulges, some part of the grain, it will form separate domains. So it will form subgrains, right? So from that subgrains, so actually the rotation is basically, it's talking about the change in the orientation. So this subgrain formation is also another process, how the deformation, deformation is accommodated within the grains, right? So yeah, and after that, what happens is that grain boundary migration. So you have the bulging, so now you applied more deformation, more stresses on that. So now it is deforming in subgrain rotation, showing subgrain rotation. So orientation change forms some new domains of grains, subgrains inside the grain. And after that, you will find the grain boundary move in certain way, like complete grain boundary move in certain ways to form separate grains, right? So those, at that time, we will see these wavy grain boundaries, right? This is called grain boundary migration. So the grain boundary migrated, and more or less in this case, the grains will be more or less strain free, right? So in case of a strain quartz, you will see undulous extinction, right? But here you can see, like in this photo, like most of the grains, the undulous extinction is not that prominent, right? It is there, it is somewhere there, and there's like here it is there, but more or less these grains are strain free, right? Yeah. So this is actually, this sums up the process. So first you have the initiation of dislocations, and then you have certain recrystallization at the edge of the grains, but which happens in a bulging recrystallization, and after that you have the subgrain rotation, and after that you have the complete recrystallization, right? So this is called the grain boundary migration, where the grain boundary migrated and formed in grains. All right. Yeah. So this will be the last part of diffusive of deformation mechanism. It is called diffusive mass transfer. So this part actually deals with different type of mechanism, different type of recovery. Um, yeah, different type of recovery that is accommodated within the grain when it is deformed, right? So it can happen in a dissolution precipitation creep, it can happen in neighbor heading creep, it can happen in a Kelvin creep. So these are the three different ways. So I think I will take one more class to explain what is the mechanism of different kinds of creep, so how this happens and all that, because it has more or less a mathematical part associated with it. So yeah, I think I will continue it in the next class. So till then, I will suggest you to go through the deformation mechanism part of the lecture, so that in the next class we can start with the creep, deformation creep, right, and the mathematical
Okay.
part.
Okay.
Okay. Yeah. So thank you
Okay.
very much. Yeah. So see you in the next
Okay.
class.
Thank you.
Okay.